How many people are here? Show of hands. How many people were out having too much fun last night? Show of hands. How many people think a show of hands is really fucking stupid? Show of hands. I was out too, so. I grew up an analog engineer. I look at security differently. I've been doing this 30 some odd years. Excuse me. Still trying to get over a cold. And the world is kind of a mess, and we've heard it over and over. Shit's broken. And what we're trying to do is the next generation firewall is going to fix everything, right? Let me show a hand. Oh, which firewall are you talking about, dude? We have to assume these days that our networks are already owned by somebody else. We have some very base assumptions that are wrong. Fundamentally, and we've had a lot of discussions in the last day or so, especially over on the steps over here, what are the metrics? How are we measuring security? And everybody's going, I don't know. So we're going to give an attempt at this to see what we can do. So this is the world I grew up in. I grew up in analog. I built analog computers as a kid. I did rock and roll, all that kind of stuff. Learning systems, learning networks, but with a different view. They were all analog networks. I didn't grow up in digital. We didn't have digital back in the 50s and 60s very much. So what is analog? And where we're going to start is just looking at this. Anybody know what that is? Is anybody smart? This is a modern gearless transmission for a car. That's it. We're getting rid of them when we get into these new generation of cars. So we do away with the gears, and so we have an analog transmission instead of a digital transmission. When we look at various things, and I know this is hard to read, but I'll give the slides to everybody. What is analog? Is a yes-no answer analog or digital? When a lawyer asks you a question, is the yes-no answer correct, or is there no correct answer that is yes or no? So part of the argument I'm going to be making is, when I'm looking at security, I want to get rid of all zeros and all ones, because they are misleading with what we're really trying to do. Analog is about continuously variable, continuously changing. Nothing is fixed. Nothing is absolutely locked in. So when we look at curves, and then we look at the digitized curves and approximation curves, we digitize them, but then we have to bring them back ultimately into an analog form, because we are analog people. That's what the nature of humans are. The other thing that happens is we have a certain quantum aspect to all of this. We have wave-particle duality when it comes to the universe and photons and all that kind of stuff. But we tend to look at security as a digital function. And what I'm going to be suggesting here is that we need to look at it as more of a wave-particle duality, where we have some digital aspects, some analog aspects, and we need to create a hybrid of the two to really get an understanding of what's going on. The other thing we need to do is look at things as a spectrum. Not just yes, not just no, but what about all of the things in the middle? And one of the things we used to do in the world I grew up in was a thing called min-max. We had a recording console, and we would want to see, does it work, does it not work, when we're testing it and all of that. And we cranked the knobs all the way up, all the way down, and we'd have thousands of knobs to do this to, which gave us our min-max conditions, which gave us a stress test in real time before a recording session or a live concert. And again, we're totally in the analog domain here, but what it did is gave us a handle on where things could go wrong. I also argue that the internet is analog. When we look at it, pull back from the zoom, when we're looking at it, is that analog, is it digital? It becomes digital when we granularize it sufficiently, when we zoom in. Nothing different than looking at a map. I'm looking at, can I see my street and my house on Google? Only when I zoom in. So there's an issue of granularity that we typically are missing when we're talking about security. The brain. We are not a computer. We are an approximation engine. When you study neurosciences, that's all we are, is some level of approximation. Your visual field only sees 2% of what you think you're seeing. The rest of it is an averaging that the brain fills in on its own to be able to give you a field of view. But we only can see really 2% of focus. And in the world that we're living in with security, we're trying to do 100% focus on things that really don't matter. So now we're tying humans and all this stuff together, and we're trying to get digital technology to talk to analog, us humans, and we're learning all over again that the language is very, very different than we had originally thought it was. So let's go back to security models, and we started talking about this a little bit yesterday. Fortress mentality, the walls, the castle. This is a binary version of, you will not come into my castle. You will not get into my network. How's that working for us? Oh, that's going well. Yeah, it doesn't work. This has been the model for warfare for 6,000 years. Build a wall high, build the moat deep, build the walls as high as you possibly can, you'll never get in, but we also know it doesn't work. It's static, it's fixed. So we've applied this kind of mindsets, and we're going to do the same thing. So back in 88, 89, Cheswick Bellevin started saying, we're going to build a firewall, we'll have rules on it, and nobody's going to get into our networks, and we also know that does not work. Please take a read of this for 1 second. When was this written? Anybody, when was this written? What? 90, no. 85, no. 1972. Is this what we're still dealing with today? The rules haven't changed, and this was the original security model by Anderson that we're still living with today, which clearly does not work. And the reference monitor came along, and this is fundamentally what it is. You have a system request, stop the process, follow some set of rules, make a decision, and it's either a go or a no-go decision. It's a very binary function. This is failed. We know it has failed, and we're still trying to live with it. So I wrote a book way back when called Time-Based Security, trying to introduce some new concepts. So in the physical world, is this vault secure? Anybody? Is it secure? You're going, yeah, maybe, maybe, maybe. That's not a yes. Is it secure? Why not? What? It's open. Perfectly good binary answer. In the physical world, we have something that we do not have in the virtual world. We have a system of knowing exactly how secure it is. And it's called ratings. In the US, we love guns, apparently. And gun safes are measured in terms of time and temperature as to how long it takes to break into it. So is it 1 hour at 3,200 degrees Celsius? Depends upon the quality of the manufacturing. But we have a fundamental understanding in the physical world of where our weaknesses are and what sort of physical power it takes in order to break through, in this case, these particular defenses. So this firewall, how secure is it? 1, thank you for that, 1. This is the approach that we're taking because we're bypassing everything. We do not, the bad guys do not go after the strongest portion of our network. They go after the weakest portions of our networks. And that's why so much of what we do actually ends up looking like this. So ultimately, how many of you have had a vendor guarantee your product? That their firewall, they're going to guarantee that their firewall is going to be good forever? Microsoft said something about Windows. Oh boy, yeah. We don't guarantee our products. There are no vendor guarantees anymore. So the question becomes, why have we spent $2 trillion in the last 30-some years of information security on products and services that we cannot define, that we do not know how strong, how resilient they really are other than just a guess, which is where we've been for all of these years. But what can we actually measure? We can't measure protection. We have no mechanism today to validate, quantify how strong a firewall is, a password mechanism is, any security protective device. Can we measure it? Right now, the answer is no. But what can we measure inside of our networks? We can measure two things. We all have some level of detection in our networks, whether it's a SIM or an IDS or an AV, it doesn't matter. We have the ability to measure certain levels of activity in our networks that is called detection. Have any of you ever measured in your networks how long and how effective your detection mechanisms are? Anybody? Why not? There is a quantifier there, and the quantifier is time. The second thing we can measure in our networks is reaction, because once I detect something, whether it's a piece of malware or a bad guy knocking on my door or whatever it happens to be, I should be able to measure how long it takes me to notice that somebody's knocking at my door, and then for me to take an appropriate reaction. How long does it take? In the physical world, there's an alarm system, and the cops are going to come. We all see it in the movies. There's somebody there with a clock. 10 seconds, 20 seconds. We have 70 seconds. Let's get out of here before the cops show up, because the bad guys can measure detection and reaction. How many of you have ever measured the detection and reaction systems inside of your networks on a basis of time? Anybody? You have? Cool, we're going to talk later. I want to learn more about you. You must be a spook. You a spook? Ex-military. Okay, so you know where this is coming from Dis and Bob Ayers' work way back when in the 90s. Excuse me. We can measure this, but we're typically not doing it in our world. In the Cold War, this is exactly what we did. We could detect a potential Soviet missile launch within milliseconds. Then we had 18 and a half minutes to determine if we were going to end the world or not. Detection, reaction, thermonuclear destruction. It's exactly the same world we're living in today, except we're not viewing it with the same kind of eyeballs that we had in the past. And ultimately, this gives us a formula. And I told you there was going to be some math in this, so hopefully I'm not going to bore the crap out of you. If we do not know how strong our protection is, there's a pane of glass, there's millions of dollars of diamonds there. There's a pane of glass there. Does that provide protection against somebody stealing that stuff? No, not really. It's, as Bruce Schneier would say, security theater. It's show. What we can measure is the detection time for the sound, the tape breaking, whatever the detection we have is, and the time for the cops to show up. What this gives us is a fundamental formula. And that formula says, if I know and I can measure how strong that glass is and how much it will defend it over a period of time against an attack, if that amount of time is greater than the amount of time it takes to detect and react to that particular attack, I then can say I have a secure condition. Very, very critical to understand this. Detection and reaction we can measure. We cannot measure protection in the current way we do things. But this formula is going to hold, and it's about a min-max condition. It's back to my old analog days. How far can I crank the knobs? How big, in this case, is my time window of vulnerability, which then leads to be able to talk to the risk people about what is the risk in my environment based upon the only metric that is potentially available to us, which is time in this particular case. So when we look at PDR, protect, detect, react, nuclear compliance, surveillance technologies, this is something that we do on a regular basis within the physical world. Why aren't we applying this in the virtual world. And for the life of me, I do not understand why we have not. Any robberies, any sort of physical crimes use, by its very nature, protect, detect, react as the fundamental formula in order to measure risk. How many of the jewels can the bad guys get in 1 minute? 10 minutes. Which leads us then to figuring out exposure time. Because exposure time, we talk about APTs. And the APTs, the bad guys have been in my network for 436 days. How much damage can they do? How much data exfiltration can occur in 436 days? Does anybody know? The answer is a whole shitload. But we don't look at it this way in terms of exposure, because ultimately the exposure time that you have in your network, regardless of your protective technology, is today purely based upon the ability to detect and the ability to react to some potential perceived or detected event. There is nothing else that we have. So given we can look at this, and these all become very simple limits, very simple calculus to be able to figure out what is the limits. And the min-max limits in this case are only two numbers. One of them is 0, and the other is infinity. Everything else sits in between. And part of our job under this schema is to compress that detection reaction time as much as we possibly can. So the concept now today is defense in depth. And again, the picture yesterday excuse me, of the castle. We have the moat and the wall and the oil and the bad guy and all that. We have all of these layers of defense. How's defense in depth working for us? I don't hear any resounding anything. All right. Defense in depth doesn't work because the bad guys, what do? They go around it. Why do you go through the thick walls when you can go around them and go through the human? And we've had a lot of discussions about this as well. So yes, defense in depth can work. You can layer it using these same types of approaches and formulas by detecting and reacting to your detection and reaction mechanisms. But ultimately, this is not going to give us what we need. So the first thing I want to approach with this thinking is, how do we kill root? I hate root. We've had root in our systems since day one when we first turned on the first password on the first mainframe computer 50 years ago. Root is also the root of all evil when we're dealing with our networks, because that's what privileged escalation is about, gaining access to the cool stuff. So the first thing we've got to do is understand a little bit of Boolean logic. Everybody good with Boolean logic? I don't need to go through it. Yes? Yeah, okay, cool. These are we're fundamentally going to deal with not, and or gates, ultimately, when we glue this together, and I show you how to make this thing all work. So the other pieces we're going to use a little bit, but not so much today. How many of you trust your significant other with your life? Show of hands. So if your wife, there's only one guy in the whole room that says this. If your wife had a choice between your children and you, would you give me the same answer? You would? So she'd kill the kids before you. So she'd kill you before the kids. Protect the kids first. So it's not a binary function. It cannot be a binary function. But in the real world, we occasionally run into this. You have to have two people sign a check in some wire transfer and financial transactions. You have to be able to have a dual authentication. And we call this binary trust. And ultimately, it's a simple function. It's a very simple function of trying to limit the amount of time that it takes for an authorization to occur. However, what happens in this case is a thing that we don't use very much, and we talked about it yesterday, was the concept of trust. Is trust a binary function, or is it an analog function? Yet, we have trusted insiders, a binary function. We have trusted executives, a binary function. Where is the weighting factor in order to be able to judge what is the level of trust? What is the trust factor? And there's different ways of looking at it. And in this case, I just gave a couple of fast examples based upon different criteria. In this particular case with the weighting factors, we wanted somebody that's really, really, really super, super geeky to be able to do stuff. And then in another case, it was somebody who was less geeky, who had a better background and had a better history. It ends up giving us a different answer. And those are arbitrary. They work within an organization. Don't try to compare trust factors of company A to company B. It's not going to work. It needs to be something that is self-consistent within its own organization. It could be just for the engineering department, just for the sales department. Fair enough. But right now, we're looking at ones and zeros when it comes to human trust versus how much do I really, really trust this person? And this is going to become very important because in the real world, we don't have one administrator in root control, do we? We have multiple administrators out of the physical necessity to be able to have coverage 168 hours a week. So therefore, root control is distributed, and it is distributed amongst a number of people. And when we look at this probabilistically, something really, really interesting happens. Because they are independent variables, we have to multiply the numbers together. And suddenly, if I have two guys with a trust factor of 0.9 each, they both have root access, and maybe one's from 8 to 5, and the other guy's from 5 to midnight. Suddenly, what happens to my trust factor overall on that root control path? It goes way the hell down. When I'm dealing with 4 or 5 or 6 or 7 administrators inside of any environment, all we're doing here is looking at a probabilistic formula to say, holy crap, no wonder stuff is going wrong. The math proves why we're having so many problems at root controls. So this is the first problem I started to look at in terms of how do I take the digital world and make it analog and come up with some ideas that may work. So what we do is, again, it's all totally probabilistic, and it ends up being common sense. The ultimate level of trust factor that you have in a root control situation is lower than your weakest link. It's not your weakest link is the weakest link. Your weakest link, your security and trust factor is lower than your weakest link. And this is purely probabilistic math. Nothing complicated about it at all. And you can learn all this stuff on Wiki. And there's just various nomenclatures for how to do this. But in this case, keep in mind, these are mutually exclusive events. Body A, body B have no necessary tie-in. Each one has independent control. Therefore, we have to look at it with this kind of probabilistic formula. So, how do we solve this? We go to what I call the 2MR, and we go back to the two-man rule. This solves everything, right? We've got to have two people do it, right? You're really going to agree with me on this? You know better than that. Don't agree with me so fast. This is the way we do it in many cases. But what happens is something very interesting. Instead of having an OR gate and applying it probabilistic that way, we end up with an AND gate saying we need both guy A and guy B to agree to a particular decision or an action. And now keep in mind, this can be a human, it can be down at the code level, it can be at the network level, it doesn't matter. These are just merely object-subject relationships that I'm talking about here. But what happens when I put in an AND gate and require the two-man rule, we end up with a different probabilistic formula, and my security goes up measurably, very, very significantly, which is very cool. However, what is the problem with this? Anybody know? What's the problem with this model? You're military, you know. What's the answer? All right, you don't know. Fine. You're not in the military anymore, are you? That's why they let you go, because you didn't know the answer. Okay. What's the problem with this? One word. What? Inertia. Not quite. Almost. Time. I get guy A to do something. I got to wait for guy B to finally get around to make a decision and agree or disagree with it. In our hyper-speed environment these days, I'm not going to be done in 20 minutes, so you better just get over it. I have to wait, and that's not going to work in today's world at all. So we're going to take another approach, and now we're going to go to the military. So, Dan, what's your name, sir? Barry, okay. You know what that means. OODA loop. Anybody know what OODA is? OODA was developed by a very, very smart guy, John Boyd, back in the 80s, and it's called Observe, Orient, Decide, and Act. And it's a circle. And the reason he came up with it was in order to be able to make fighter pilots understand their environment, that they had to go through this cycle on a continuous basis. And that increased survivability, likelihood of success in air combat. And the same thing works in marketing. I got an idea, I'm going to test market it, I'm going to build and sell some, I'm going to see what the market says, now I'm going to modify it and do it all over again. It's an iterative, analog process, not a digital process. So what I like to do, again, is apply a functional limit to this. Can I ever, in an OODA loop, whether it's warfighting, marketing, decision-making, and networks, can I ever reach zero time? No, of course not. So I have functional limits and bandwidths and constrictions that are naturally part of the environment that I need to consider when we're looking at what I call squeezing the loop. And this is the issue that we call in our world granularity. And the granularity could be the quality of the audio based upon the compression algorithms, or in this case, it's a purely analog function of squeezing time, trying to make the OODA loop as granular and as small as I possibly can. So we take that, excuse me, and then we look at the real world. We have subloops. In the observe area, we're going to have a lot of little sub-areas. I'm going to observe this, I'm going to observe this, I'm going to observe this. I'm going to have different takes based upon my detection. Observation and detection are the same type of function. So if I treat it from an analog standpoint, I'm going to have all these little processes going on. In software, we call them subroutines. Same thing. It's a matter of how you view it. And ultimately, what we do is we can apply fractal mathematics and Mandelbrot sets to this and start examining how deep the granularity is of my observation and my detection systems. It's all about the detection, nothing else at this point. So now we're going to go into the most critical area of this. I grew up an analog engineer. In the real world, this device, anybody know what it is? Shout it out. It's called a governor. It keeps steam engines from running too fast. We heard it yesterday at the ladies' talk. Feedback caused by the microphone and the speaker having what's called positive feedback. And down here is an electrical circuit. What feedback is one thing and one thing only. It's a mechanism to control and stabilize a network. Now, that network doesn't have to be a digital network. It could be a conceptual network. It could be the acoustic network. It could be a physical network. And so we have an abstraction here that tells us exactly how, mathematically, to define our feedback. The whole point is, every engineering discipline in the world, with the exception of information security, employs feedback. Why? Why? We're still naive in believing that we've got this binary function. I'm secure. I'm not secure. And that's what the risk guys, that's what the CISOs, that's what these guys all want to hear. They don't want to know about the feedback mechanisms to be able to actually control them. We have it in our lives, haptics. You touch the key. Anybody ever have one of those keyboards and it doesn't give you anything back and it's like, what the hell? This is a shitty keyboard, right? You want to have some feedback so you know what's going on. You want to be able to smell. It's about sensory input to us as human beings But we're not doing this in our networks, even though the networks are tied to humans and technology. Zero feedback mechanisms built into our networks and designs today. Holland, for you guys from the Dutch lands up there, they survive, their country survives because of the Delta Works. And it's a feedback mechanism in order to keep the North Sea from inundating their entire country. Started building it in the 50s, and it works amazingly well. Any feedback mechanism is designed to prevent chaos from ensuing. So how do we apply this? Let's just take a real simple example here. We're going to have some process request. Again, is it a human request? Is it a digital request? Doesn't matter. What I'm going to do is begin this process, but what I'm also going to do is begin a clock. I'm going to start a clock, and we're going to arbitrarily say, for example, that I want to have that particular process approved. Alice makes a decision, but I want Bob to approve it within 1 second, 1 minute, 1 hour. That's a policy decision based upon the trust factor of Alice and Bob, and back to our probabilistic numbers that we had earlier. And with using those numbers, I now have quantifiable numbers based upon time. So the exposure time that I showed you earlier becomes the exposure during that feedback loop that we would have here. And in this case, this would be, again, a simple abstraction of it. But when I apply the feedback loop, I now can have a very, very specific level of trust factor defined over a period of time, which tells me what my risk is. My risk then is a function of time and trust factor, both of which are analog functions. Neither one is digital. So we can do the thing, we can do it with enforcing two-man rule, very, very simply. We can do it with INA mechanisms, same approach to it. They're all fundamentally the same. And occasionally you may run across this when you're on mobile banking, and it says, oh, this is a new device, please go check that device over there and make sure, then you validate the code and come back in. And you have X amount of time to do it. It's exactly the same process, so we're seeing a couple of these in the real world now, especially in the mobile. Now, in the time-based reference monitor, we go back to the reference monitor work from Anderson back in '72 and say, God, I hate this. What we do is we have a system request, pause process. Instead of stop process, we want to do pause process. Because if we have properly designed our network and our detection and reaction system, we know how long it takes. How long does it take to know if a particular piece of code is bad or not based upon our lookup tables? You know the answers better than I do. Is it 1 second, 100 milliseconds, whatever it happens to be? So the lookup tables are based upon time. Go, no-go decision is made based upon that. But what happens as a result is by adding in the pause, I've reduced the amount of risk that I've got because I'm not allowing that particular action to occur. And I'm going to show you the formulas for this in a couple of minutes. So now we're going to go down to a little more feedback. Does anybody know what this is? Anybody? What? Shout. Okay, this is called an RS flip-flop. It's a feedback-based mechanism that is the fundamental of everything we do in the world. That is a bit of memory in digital logic representation. So basically what happens is if I set R, Q will go high. If I set S, Q will go low and Q prime will go high. It's merely a bit flipping, bit of memory. That's all that it is. And there are corresponding truth tables to that tell us exactly how the system works. This is the digital representation of how we do things. But now let's redesign this circuit a little bit and add a clock. We add a clock into either the A or B input, doesn't matter, the S or R input. And what we do is merely say, unless an approval is commenced within X period of time determined by policy, we revoke the prior decision. Very simple. Unless the approval of a particular action at the code level, at the human level, at the G to G level, doesn't matter, occurs within a very specific policy set of time, revoke that decision. That now, because I'm in the detection and reaction world, I know exactly how long my exposure time, and I can then translate that into risk. There are corresponding truth tables that we've been able to develop out of using an analog feedback in what we call a time-based AND gate or a time-based flip-flop, depending upon which terminology you're more comfortable with. So how do you launch a nuke? This was something that we figured out 40, 50 years ago, and the circuitry is very, very similar. What we have is two guys that are willing to blow up the world sitting down underneath some silo in North Dakota. They have independent clocks, and either one of them can initiate to launch the nukes. However, the key is, some people say, oh, they have to do it at the same time. No, they have to do it within a particular window of time, and that window of time is typically less than 2 seconds. They both have to flip that key, and this is exactly the same circuitry that we have never applied to information security, to get agreement based upon time on what your policy and the invocation of any of the attributes that you're going to have for any security at all. We've had this in the physical world for more than 50 years. We have not done it in our world. So then now the last piece of this is going to be going out of band. And in my old world, when we started doing automation in the audio world, we used to have the same thing the TCP IP does. I got one wire that has data and control signals. Well, that's sort of cool, right? In our world, we had an audio signal. In the middle of the audio signal, we had a volume controller, an equalizer, and we could adjust the signal. Along came, let's automate all this, which meant that we needed an out-of-band control signal to be able to control the actual signal flow itself. The cool part about that meant that if I lose my control path, the signal remains where it was. It doesn't go away. It's not disappearing. It remains where it was prior set, like memristors do with memory right now. So in our world, we got all of this stuff on one wire. You cut that one wire, you're shit out of luck. It all goes away. We don't have an out-of-band condition. So this is what a detection reaction module would look like, where we have monitoring an asset, some level of detection. Doesn't matter what it is. Again, I don't care if it's code, if it's human behavior. This is a pure abstraction. We have reaction matrices to make decisions as to what should happen, which is called pre-thinking out your world. Analyzing, somebody mentioned yesterday, what could go wrong? How much thought has gone into what could actually go wrong, to have some sort of preparation when those things do go wrong. And then you're going to have reaction out to a reaction channel. Some decision will be made based upon time because it's all clocked entirely. And then you're going to enforce that reaction. And then enforcing that reaction could be turn it off, turn it on, call the administrator. It doesn't matter. This is a pure theoretical abstraction of how to control a network flow and vulnerabilities based upon time. So you've got to obviously have some idea of what you want to do, and this requires thinking, absolutely. But for those organizations that instantly have a problem and call the FBI or their lawyers, you guys are idiots. That's like wrong. You got to have some idea of what you're trying to do when the shit hits the fan. So a simple reaction matrix is just having, in this case, a bunch of perimeter stuff going on. I got a bad guy knocking on my door. Very, very simple. Now, I can also complicate it further by having multiple reaction matrices, some on an internal basis without a band security, and some going on perimeter, and they can talk to each other. Again, it doesn't really matter because the abstraction of the reaction matrix sitting at the detection points in the network and having a reaction feeding back into it on an out-of-band mechanism does not interfere at all with the primary functioning of the network. It's completely separate. So I don't have to redesign TCP/IP to make any of this work. This is a 777 engine. The reason the picture is here, inside of this engine, there are 5,000 detection points. 5,000 that are monitored and updated every single second to optimize performance. How about our networks? We doing anything like this? This is GE and Siemens are the two companies that are leading in the ICS, Industrial Control System world, of providing feedback into systems to be able to create stability, measurement, and true control. The object is, in my mind, not defense in depth, it is detection in depth. How many places in your networks should you be looking for something going wrong? 1 place, 2 places, 10 places, 1,000 places, at every bit, at every decision point? Doesn't matter, because ultimately it's a matter of policy and the level of depth of security that you're trying to achieve, and ultimately the numbers will fall out as a function of time. But it's detection in depth is where this industry has completely failed. We're not looking at what we're doing. We're looking at the input, we're looking at the output, and we're not looking at anything in the middle, which from an engineering standpoint is a recipe for disaster. So one of the things that we can do with this approach is actually solve denial of service. That'd be kind of cool, wouldn't it? And all we're doing basically is having out-of-band communications occurring, assuming that in a DOS attack or DDoS attack of any sort, my primary communication and control channel are going to be full, because that's what the bad guys want. They want to put me out of business. So one wire, bam, they're nailing it. But if I put this all the way around on, imagine that every tier 1, tier 2, and tier 3 ISP in the world had back-channel communication. And all it does is say, I am detecting this, and I'm detecting bad traffic from this IP address. And I communicate down to the next hop where that traffic is coming from, because I know where it is. My primary channel is already full, so I have to go out of band. I can tell the next hop, stop this. Then that hop will know where its traffic is coming from, whether it's distributed or not. And we have a complete back-channel communication system going on outside of TCP/IP without having to modify it either, in order to be able to allow this to grow. The same thing will work for spam as well. And ultimately, what we're looking at is our primary network is up there. Standard network, that's everything we live with today. And I'm suggesting that if we add detection reaction modules, not a lot of code, detection reaction modules, in this case at the network level, it could be at the code level as well. I want to know what's going on, when it's going on, and have a backplane of communication to tell me what is my network actually doing in real time, plus or minus a few clock cycles. And this is the model that we've been working with for the last couple of years to try to get this built, which is a new protocol for out-of-band communication for detection reaction matrices, so that we have a completely separate, policy-driven set of rules outside of my primary stack and communication channel that are still able to out-of-band control what's going on. So one of the things that we can do here is start looking at where are my targets. And again, simple math, because everything is about time. File size is time. Bandwidth is time. Everything in our networks is about time, yet we ignore it. The only thing we care about is, does it work? Does it not work? Again, this is very, very simple. So what can I do with this particular case? Why don't I add what we used to call in my world a compressor? Something bad's going on. We're worried about data exfiltration, perhaps. Why don't we add what we would call an attenuator or a volume control, and it ends up constricting data? Why not just slow the data? Why do I have to stop the data? Do I need to have a binary condition at all times when something goes wrong? And I argue no, that there are variables in the middle. And it's a very, very simple bandwidth constriction module that can go into any pathway at all, and we just call them compressors. But you can end up with orders of magnitude of improvement in measurable security if you have a detection reaction matrix and one of your modules, inline modules, is actually a compressor. Now we're going to really screw with you, and we're going to do something called negative time. Again, back in my old world, we had audio. Now, anybody remember Led Zeppelin? Yeah. And you remember A Whole Lot of Love, and whoa, 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 and the voice, and it was echoing and all that. We did that by having a tape machine over there and a tape machine over there, stringing a piece of magnetic tape between the two and adjusting the distance between the machines in order to create those delays. That was the technology of the day in the late 60s. It ultimately became called a digital delay line. And a digital delay line is nothing more than a delay of a digital component over a period of time again. So what I want to do is add negative time into some networks. And why do I want to do this? Because it gives me mathematically provable security. I can prove security by taking this approach. And ultimately, if we know our detection time and we know our reaction time, we know that protection is indeterminate. We can't prove that given existing technology. But I add negative time into the data flow. What ends up happening? I end up with a mathematically provable formula that says that that particular component of my network is mathematically provably secure. I know I'm going through this really, really quickly. This is normally 4 hours. Here's one example of how to do it in the data compression mechanism. Detection reaction, we've got a detection reaction master control, of course. And in this particular case, something goes wrong, and we're doing a data compression, in this case, 3 orders of magnitude. Fair enough. We can apply this same approach with the negative time as well. And in this case, how do you stop phishing? This is the model on how to stop phishing using this approach. And we have the technology. We understand enough of the mathematics now to be able to actually make this work. Oddly enough, and I did not know this until a couple of months ago, for those of you that are familiar with load balancing and queuing, the formulas are virtually identical. And I didn't know that. It was like, oh, wow, that's kind of cool. I found something. The approach is the same. And it's looking at min-max conditions with time as being the fundamental metric for all measurements throughout. So what else can analog network security do for you? I don't know all the answers at all. I know some of the things that I have found, lots of cool things that have appeared and shown up that, wow, that'd be really cool if I could do this and do this. And this is why hopefully we'll get the industry to start looking at some of the things that we can do. These are the tenets that I live by. And one of the things I'm going to suggest to you, whenever you have a discussion about security with anybody, whether you're asking the question or answering the question, make sure that a time component is part of either the question or the answer. If you do not invoke time, you're going to fail because you're looking for a binary answer, not an analog answer, because there is no such thing as a 0 or a 1 when it comes to security. It's always something in between. So use time in every discussion you've got. I got a new book coming out. Please buy it. Thank you very much. And I know I went over 4 minutes. You guys have been awesome. And I know this was a 4-hour thing, and I had to do it really, really fast. I'll be here for the whole day if anybody really wants to sit down and start drilling with the math, and I'll show you how it all works. Thank you very much. I appreciate it.
Thank you so much, Winn.